In this video, we're going to cover section 3.4, again on Bronsted-Lowry acidity like we saw in the previous video, but now we're going to approach acidity from a qualitative perspective. That is, we're wanting to compare acids without using pKa tables or pKa values. So how we do that is we look at the relative stability of the conjugate base for the acids that we're comparing. And if the conjugate base is very stable, i.e. it's a weak base, then the acid from which it came must be strong. However, if the conjugate base is very unstable, meaning it's a very strong base, then the acid from which it came must be very weak. So we can use this approach to compare the acidity of two compounds by comparing the relative stability of their respective conjugate bases. So if we compare the relative acidity of HCl versus that of an alkane, shown here, pentane, what we would do is we would look at their conjugate bases and compare the relative stability of the conjugate bases of those two, what we're calling here, two compounds, two potential acids. So HCl, the conjugate base of HCl, is the chloride ion. So chlorine is quite electronegative, and so because of its electronegativity, it's able to stabilize that additional electron fairly well. So due to the relative stability of that chloride ion, we would expect that the acid from which it came, HCl, is quite strong. Now, if we look at the example below where we have our alkane, if this alkane were to lose a proton, the respective conjugate base for it would be an alkanide. Now, carbon, on the other hand, relative to chlorine, is not nearly as electronegative. So its ability to stabilize that additional electron around its atomic center is not as good. We would say, based on the differences in electronegativity, that the chloride will be more stable than the alkanide. So the carbanion is going to be less stable than the chloride ion. So as a result, the more stable the conjugate base, we'd expect it to come from a stronger acid. And we know from our previous video that yes, HCl has a pKa well below 0, -7, whereas the pKa of an alkane is typically around 50. So based on the relative stability of the conjugate base, that gives us insight into the relative acidity of the two original compounds that we're comparing. In this example, we use the relative stability of two atomic centers with an additional electron as a way to describe or assess stability. So in this example, we really only had to look at the relative electronegativity of the atom, which was taking on this additional electron, this negative charge, to determine the relative stability of the corresponding acids. There are other factors that can be useful in determining the relative stability of a conjugate base, and those factors that affect stability are atom, as we saw in the previous example, but there's also resonance, induction, and orbital, which also play a role in the relative stability of conjugate bases. So what we'll do now is we'll go through an example where each of these factors plays a role in affecting the relative stability of the conjugate base. So atom, as we saw in the previous example, we need to consider which atom is the charge on. So in this example, if we're comparing butane with 1-propanol, if we want to compare the relative acidity of the hydrogens that are highlighted here in red, what we do is we look at the conjugate base of each of those corresponding acids or compounds. So for butane, that's going to give us this butanide ion. So this is the alkanide for butane, where it'll be the terminal carbon that is going to take on that additional electron with the loss of this particular proton. So we deprotonate each of these two acids and look at their two conjugate bases. So when we compare these two conjugate bases, the only difference is the nature of the atom, which has that negative charge. So when we look at the atom that is taking on this additional charge, the main factor that is going to determine the relative stability of that anion is the electronegativity of the atom, which is taking on this additional electron. So as we've discussed previously, electronegativity measures an atom's affinity for electrons, or how willing the atom is to accept that new electron. So we know from our periodic trends that electronegativity increases as we go from left to right within a particular row of elements. And so if we compare the electronegativity of carbon versus that of oxygen, we know that oxygen is more electronegative due to its placement in the periodic table. That being said, that would imply that due to the higher electronegativity of oxygen relative to carbon, that oxygen is better able to accept that new electron from the loss of the original proton of that alcohol. So if this oxygen is better able to accept, or more willing to accept, that additional electron, it's more stable than the corresponding alkanide. If this is the more stable conjugate base, then we know that the corresponding acid, that is 1-propanol, will be the stronger acid relative to butane, which was the other example. Now let's look at another example where we compare water with hydrogen sulfide. And so the conjugate base of each of these two species is shown below. We have the hydroxide ion and the hydrosulfide ion. So when we compare the relative stability of these two conjugate bases, electronegativity ends up not being the dominant effect when the elements that you're comparing are not in the same row. So instead, the dominant effect is size. So again, we know that electronegativity will increase as we go from bottom to top in our periodic table. And so it would seem to imply, based on electronegativity arguments, that oxygen would still be the more electronegative atom over sulfur. Now, that is true, but that's not the dominant effect when it comes to comparing elements that are not in the same row. So sulfur being in the third row, oxygen in the second row, a much more dominant effect is the actual size of those elements, or the relative size of those elements. So as we go down the periodic table, we know that the atoms are increasing in size as they're incorporating more and more electrons. And so the size of sulfur is greater than that of oxygen. So how does that have an important role? Well, with sulfur being larger in size, it has more space, if you will, to spread that charge over that atomic region. So there's a larger volume of space to spread that additional electron around a sulfur atom than there is around the oxygen atom. So due to this effect of size, the hydrosulfide ion will be the more stable conjugate base relative to the hydroxide ion. So if the hydrosulfide ion is more stable, that would imply that H2S is a stronger acid than H2O. The next factor that can affect the stability of a conjugate base is resonance. And so when we're looking at the relative stability of a conjugate base, we need to consider whether or not there's any resonance effects that makes one conjugate base more stable than the other. So if we look at this example of ethanol versus acetic acid or ethanoic acid, if we compare the relative acidity of these hydrogens, to do so, we look at their respective conjugate bases. So again, this will be an ethoxide ion, as shown, and this would be the ethanoate ion, or often referred to as the acetate ion. And so in this example, because both atomic centers are oxygen, there is no difference in atom, and so we can't go to the atom effect to determine the relative stability. We must consider some of the other factors in our list. So when we look at the ethoxide ion, we can't draw any resonance structures because the charge is localized on this oxygen center. Whereas with respect to the acetate ion, the ethanoate ion, we can draw a resonance structure for it. You can see that this original form can be redrawn by delocalizing the electron density to form a new pi bond here and breaking of this pi bond to give you a new oxygen-centered anion or oxide. So again, using our Curved-Darrow formalism, we can show that we do in fact have a resonance stabilized entity. And so due to that additional delocalization that can occur for the electron that's found in that oxygen center, due to that delocalization, which is in effect resonance stabilized, this will be the more stable conjugate base. So therefore, the acid from which it came, acetic acid or ethanoic acid, it would be the stronger acid relative to ethanol. And in fact, we know that's the case, that the pKa of acetic acid in our table was listed as 4.75, whereas the pKa of ethanol was 16. A third factor that can affect the relative stability of a conjugate base is induction. So the question we ask is, are there any inductive effects that stabilize one of the conjugate bases over the other? And so the example we'll use to describe induction is comparing acetic acid, the acidity of it, relative to trichloroacetic acid. And so if we look at the conjugate bases of each of these species, we have the acetate ion and the trichloroacetate ion. Now, when we compare the atom effect and resonance effect in this example, we see that both conjugate bases are stabilized by resonance, and both conjugate bases have a negative charge on the same type of atom, oxygen. So neither of those two factors are going to allow us to determine which acid is indeed stronger. So this is where the inductive effect comes into play. So induction is really the ability of atoms to withdraw electron density from neighboring bound or through bond neighboring atoms. And so the net effect of the chlorine atoms in trichloroacetate is to withdraw electron density away from the negatively charged region of the compound, that is, where that negative charge on the oxygen center is lying. And so this ability to withdraw electron density away from the delocalized electron density in this part of the molecule is going to provide an additional stabilizing effect. So as a result, the trichloroacetate is more stable due to the presence of these chlorine atoms and their ability to withdraw electron density from this delocalized additional electronic charge of the acetate ion. And so because this is a more stable conjugate base due to induction relative to the acetate ion without those chlorine atoms present, the stability, the enhanced stability of the species would imply that the acid from which it came is stronger. And that is in fact the case. Of course, if we compare the relative acidity of acetic acid to various chlorinated derivatives, we can see that as we add one chlorine to the carbon next to the carbonyl, we have a reduction in pKa of almost 2 orders of magnitude, so almost a factor of 100. If we add a second chlorine atom to that same carbon, we see further reduction. And then finally, the trichloroacetic acid is the most acidic of these variants with a pK of just under 1. So with each additional chlorine atom, the compound, i.e. the original acetic acid, becomes more acidic. The last factor that we may have to consider when looking at the relative stability of a conjugate base is that of the orbital. And the question we ask is, what orbital do we find the negative charge for each conjugate base? So in this example, we're going to look at this enine structure. This is called an alkenine because it has both the alkene functional group and an alkyne functional group in the same compound. And so in this example, we're going to compare the relative acidity of these two hydrogens. And so we're going to look at, somewhat independently, what would the relative stability of each conjugate base be if in one example we were to lose this particular hydrogen atom as a proton to give us this particular anion, versus if we were to lose this particular hydrogen as a proton to give us this anion. So in this example, we see that the conjugate base for both examples would be a carbon-centered anion, so a carbanion. And so if we look at our previous factors, the atom is the same. We cannot draw resonance structures for either of these conjugate bases, and there's no inductive effects present. So the orbital effect is to consider which orbital is taking on this particular electron. So for that, we need to determine what is the hybridization of this carbon versus the hybridization state of this carbon. So in each of these carbanions that we're comparing, what we need to consider is that a pair of electrons in an sp hybridized orbital is held closer to the nucleus than a pair of electrons in an sp2 or sp3 hybridized orbital. As a result, electrons residing in an sp orbital are stabilized by being close to the nucleus. So what's being shown in this figure are the relative shapes of the sp3, sp2, and sp hybridized orbitals. And when we compare their relative shapes, we see that as we go from sp3 to sp2, the length, if you will, this distance here for the orbital shortens and the width increases. And that's because this sp hybrid is made up of a mix of an s and a p orbital. And so 50% of what went in to the mathematical model, which describes the shape of this sp orbital, came from an s orbital. And remember, recall that the s orbital is spherical in nature. And these spherical orbitals, s orbitals, because of their shape, electrons found in these orbitals are fairly close to the nucleus. So when you have a hybridized orbital that has a greater, what we say, s character, meaning there's 50-50 mix of s and p that give rise to this particular orbital, because of that additional s character, the electrons found within that orbital are going to reside more closely to the nucleus, and that is going to enhance the stability of that carbanion. Whereas for an sp3 hybridized center, because there were 4 orbitals that went into the mix to make this particular hybridized orbital, there is s character, but it's significantly reduced. It's only 25% of the total number of orbitals that went into this mix. And then the sp2 would be more like 33% of that orbital is coming from that s orbital. So the sp is going to be able to stabilize the additional electron on that carbon center more effectively because the electrons will be closer to the nucleus. So as a result, we would expect that the acidity of the alkyne end of this molecule will be higher because the stability of this additional electron on carbon in an sp hybridized state is going to be more stable than an electron on carbon that has an sp2 hybridized state. And here you can see below, if we compare the 3 simplest hydrocarbons that represent the alkane, and the alkyne, we see that the relative acidities, the alkanes closer to 50. When we have ethene or ethylene is its common name, we see that we have a reduction in acidity by a factor of 1,000,000. And then when we get to acetylene, we have a significant difference in the pKa. And again, in all these cases, carbon is the atom. There's no resonance effect. There's no induction effect. So the orbital is what plays a significant role in affecting the relative stability of the conjugate base, and in a sense, directly relates to the acidity of the original hydrocarbons. So that concludes the factors that we consider when assessing the stability of a conjugate base. And in general, the order of priority is the order in which the factors were presented. That meaning that the atom is the most important factor, followed by resonance, then induction, and then the orbital effect. And these four factors combine to give us this abbreviation, ARIO or ARIO, and this is what we typically use in our qualitative perspective or qualitative approach to assessing the relative acidity of two compounds. So let's look at an example where we have, in a sense, competing factors in our examples. So here in this first example, if we compare ethanol to that of propene, common name propylene, we see that the conjugate base of ethanol we've seen before is the ethoxide ion, and that for propene is this propanide ion. Now, in this particular example, if we look to our first factor, atom, we see that with the ethoxide, the additional electron is associated with an oxygen center, versus propene, that additional electron is associated with a carbon center. And so carbon being less electronegative than oxygen, just using the atom effect, we would say that the ethoxide ion is more stable than this propanide ion. And as a result, we would expect ethanol to be a stronger acid. Now, yes, it's clear to see that there is a resonance effect that could be drawn, or I should say a resonance structure that could be drawn for this particular conjugate base. But again, because resonance is, in the sense of our order of priority, second compared to the atom effect is going to be the predominant effect that gives rise to the stability of the conjugate base. It's not to say that this doesn't enhance the stability of that conjugate base. It does, certainly does, but because it's a carbon-centered anion, a carbanion, relative to an oxygen-centered anion, it is less stable based on that particular fact. So when we compare the table values for ethanol and propane, we do see that, in fact, the pKa of ethanol is significantly lower than that of the alkene. Now, there is one exception to the ARIO system that I want you to be aware of, and that's shown in this particular example. When we compare acetylene or ethine, the simplest example of an alkyne, with that ammonia, NH3. So when we look at the conjugate bases of ethine and ammonia, we end up with the ethynide ion and what's called the amide ion. And if we were to use our ARIO system, the first factor to consider is the nature of the atom, which is taking on this additional electron, taking on this additional formal charge of -1. And so if we were to compare the carbon in the ethynide to the nitrogen in the amide ion, we would say that the amide ion should be more stable based on the fact that nitrogen is more electronegative than carbon. As it turns out, experimentally, the acidity of these two species, ammonia and acetylene, do not follow the ARIO system. In fact, the presence of this sp hybridized system of the ethynide ends up being a more dominant effect than the atom effect associated with the amide ion. So what we observe when we react the amide ion in the presence of ethine is a reaction that is in equilibrium but is significantly favoring the forward direction in the formation of ammonia and the ethynide ion. So as you can see in this reaction, the pKa of ethine is 13 orders more acidic than that of the conjugate acid, in this example, ammonia. And so this is the one exception to the rule to the ARIO system that we need to remember. As a side point, we'll see this later on in the course when we look at the reactivity of alkynes. That is typically the amide ion that is used to deprotonate terminal alkynes in the formation of these alkynide ions. So it will be a very useful reagent for those types of reactions when we get to that section. So let's look at an example where we can use the ARIO system to determine the relative acidity of two hydrogens found within the same molecule. So in this example, we have two hydrogens that we're going to compare. We're going to compare the relative acidity of this hydrogen attached to this oxygen atom and the hydrogen attached to this sulfur atom. And so in order to compare the relative acidity of these two hydrogens, we need to look at their respective conjugate bases. So we can redraw the two possible outcomes. One where we have the loss of a proton from the OH, the acidic part of this molecule, and the second where we have the loss of a proton from that sulfur hydrogen bond. And so when we compare the relative stability of these two possible conjugate bases using the ARIO system, the first factor that we need to consider is the atom. And so in this structure, the atom is oxygen, and in this conjugate base, our atom is sulfur. And so you may recall from earlier in this video that we used either electronegativity or the size of the atom to determine which atomic center will have a greater stabilizing effect. If the atoms that you're comparing, elements that you're comparing, are within the same row of the periodic table, electronegativity is the dominant effect. If, however, the elements are in the same column or the same group in the periodic table, then size is the dominant effect and not electronegativity. So because oxygen lies in the same group as sulfur, but lies above it, we know that sulfur is greater in size relative to oxygen. And so the additional electron that's left after deprotonation of this particular molecule on the sulfur atom is better stabilized by the sulfur atom than the oxygen atom. So in this example, we don't need to look at other factors such as resonance, induction, or orbital. In fact, the orbital is going to be similar, and resonance is also possible in both of these examples. In this example, we have a resonance effect which delocalizes that charge between those two sulfur centers. The same thing can be shown for this particular part of the molecule, that we can also delocalize this additional electron density over these two oxygen centers. So they both have resonance effects that help to stabilize these conjugate bases, but the main difference is the nature of the atom. So because this conjugate base is more stable than this conjugate base, this hydrogen atom would be considered more acidic. So that's the qualitative approach that we will use to describe the relative acidity of organic compounds. And if you have any questions about this video, please send me an email or start a discussion in our forum. Thank you.